Good morning, everyone, and welcome to Fun Science Morning. I'm Dr. Iski, and this is
Dr. Kevin.
to give you a little background behind our interest in science. I teach chemistry at the University of Tulsa. I've taught chemistry there for 7 years. I'm also originally from Tulsa, and I went to Booker T. Washington High School. Kevin, what's some of your background in science?
I'm a podiatrist, and I just have an ongoing interest in basic sciences.
Awesome. Today, we're hoping to do some very fun experiments for you. We're going to try our best to break down both the chemistry and kind of the cool observations that you'll be seeing today. We're going to have 2 chemistry demonstrations that we're doing, and we're also going to be explaining something super cool that Dr. Kevin brought us. And what is that?
Brought dry ice.
Dry ice. So we're going to finish the entire session by looking at dry ice and some of its cool properties. So we really would like you to hang on for the full session with us. So that's 2 chemistry demonstrations ending with some CO2. Super exciting. We're so glad to be here with you today. Our first experiment is something that many of you have probably dealt with or at least seen on TV, perhaps on Nickelodeon or something like that, and that is slime. So we're going to start today by making some slime. What are your feelings about making slime, Dr. Kevin?
Very excited. I haven't done it since grade school.
Yeah,
so
super exciting.
Good reintroduction.
Everyone loves to get their hands dirty, and that's what we're going to be doing now. So first, what we want to do with these demonstrations is give you an example of how you might be able to do them when you're at home. So the idea is that you can do both of our demonstrations today at home anytime you get bored, anytime you're interested in doing some chemistry with your parents or your brothers and sisters. So let's start now, Kevin, with our ingredients for slime. Our first ingredient is very, very simple. It's something that your parents should be able to get at any store, and that is just regular Elmer's glue. In general, there doesn't need to be anything special about this glue. In fact, just kind of regular white school glue will do. So that's pretty awesome. Okay, so that's our glue. Our second very important ingredient for our slime, it's going to be something called borax. So hopefully you can see that here on the camera. Borax, kind of a fancy name for simply soap, right? And what's one of its main uses, Dr. Kevin?
I like to use it to clean the floor in the shower.
Absolutely. This is a well-known cleaning detergent. It does a great job at disinfecting and getting that done. So borax and glue are 2 main ingredients here. We're also going to need some water. Very exciting. Water. Now, before we get into the actual demonstration, we're going to break down the chemistry that's going behind making this slime. And that is that slime, once it's made, once we have it in our hands, it's something called a polymer. A polymer. Now, a polymer is simply made of 2 smaller units. And what do we call those smaller units?
Monomers.
We call those smaller units monomers. And what we're going to do now is we're going to use some Legos to kind of make an example of how you would think about looking at a monomer as an individual unit. So we have our Legos, all right? You can hold them up. Hopefully you can see these. So these are just kind of your run-of-the-mill Legos. But what we want to think about here is that each one of these, so this blue unit, this red unit here, other blue unit, these all represent what we call monomers, all right? So individual, they can exist in perpetuity on their own. What we want to do, though, when we're making the slime, so my group of monomers is going to represent the glue. Your group of monomers is going to represent the borax solution, right? 2 separate monomer units. Now, what's going to happen, Dr. Kevin, when we mix these monomer units together?
They're going to form a polymer.
Exactly. So we're going to add them together. There you go. To make a final structure, we've got all of our subunits are still a part of this polymer, but we're making one new unit. And what's really, really cool about this new unit, this polymer that we've made, has totally different properties than the two separate monomers. You ready to do the experiment, Dr. Kevin?
Let's get it on.
All right. Because we're scientists and we always take into safety precautions, we're going to put on our goggles. You don't necessarily need to do this at home, but it is kind of fun for us. All right. So what I'm going to do here is I am going to take a teaspoon, not even sure if you can see that, but this is our borax solid, okay? And we're going to take a teaspoon. You can get this from your mom's cooking supplies. A teaspoon of our borax into one bowl. We're then going to pour a cup of water. Actually, do you want to do that? Here, I'll hold that. So we're going to pour a cup of water into our borax solution. So there's 1/2 cup there, and I know you can't see this, but kind of like imagine it in your mind, if you will. So we're adding 1 cup of water to our solid borax. Dr. Kevin is going to stir this solution. You want to stir this such that your borax becomes dissolved. Get that out of your way. So you're going to make that dissolve. I'm actually going to take those off temporarily. All right, so while Dr. Kevin is dealing with the borax solution, I'm going to get messy over here, and I am going to start making my glue solution. In order to do that, we take a 1/2 cup of the Elmer's glue. This is where it gets really messy. You can see it pouring out here into the 1/2 cup. We're going to pour that into another bowl. Very exciting here. I apologize if you can't see this, but we're pouring the glue into the bowl. Your next step here is to pour, I believe, a 1/2 cup of water into our glue solution. So I've got some more water, another 1/2 cup. That's going into our glue solution. All right. Let's recap what we're doing here. Dr. Kevin has the borax solution that he is stirring vigorously. I separately have a glue solution. Not sure if you can see this. It's just glue and water. And I am stirring this, mixing these together. Kind of looks like a soup. Now, as chemists, we want to ask ourselves, we want to define each of these solutions before we put them together. So let's ask Dr. Kevin, what does your solution look like? Because we can't see it on camera.
It is a cloudy looking water, whitish in color.
And is it viscous or is it pretty thin?
Pretty thin.
Okay, so it's a thin, not too thick liquid. My glue solution is actually pretty liquidy as well, even though it has glue in it. Because of that 1/2 cup of water, both of these, I would say, are pretty liquid-like. Now, Dr. Kevin, could you please add some food coloring to our glue solution? What color are you going to choose for this rainy day?
Blue.
Okay, we're going to add some blue, kind of see if we can dramatically add that to our glue. Oh, it's so exciting. I love food coloring. Let's get crazy. Put a lot in there. Perfect. Awesome. Oh my gosh, I wish you guys could be here to see this. It's so blue. I think that's good. Dr. Kevin went a little bit crazy with our color, but hopefully you can maybe see that as I try not to spill that into the camera or onto the table. We've got our blue solution. We've got our borax and water solution. Remember, we want to think about these two as a monomer unit on its own and another monomer unit on its own. These are our separate Legos. Now what we want to do, and perhaps if we were really good, we might be able to pour this into this beaker here. I'll go ahead and pour in my glue solution into the beaker. We're adding our glue solution. It's nice and blue because of the food coloring. Really exciting. All right, Dr. Kevin, you are ready to add the borax, and you'll just, once you add that, you'll stir it together. I know it's a little bit trepidatious. We're pouring the borax. Fantastic. And now what we're going to do, kids, we're going to stir it together. And that's good. That's fine, yeah. As we're stirring this together, what's happening here, Dr. Kevin? What's happening? Kind of pull that stir rod out. What is that? What is going on in there?
The viscosity is increasing.
Oh my goodness. I think we might be making a polymer, perhaps. Am I right?
I concur.
So what are we making? Look at this, you guys. We added 2 very liquidy solutions, and now we're getting this very different, very thick kind of glob, I would say, perhaps is forming in there. Now let's get even more crazy, and let's pull that glob out, and let's get the water out of it with your own hands. Somewhere at some point we'll get some paper towels for Dr. Kevin. All right. It's okay if you drip. So here we go. Oh, you guys, wait till you see this. This is exciting. Look at this. Now, yeah, just mix it around with your hands. Oh, you're getting all of it.
We got more glob.
Oh gosh, we've made a lot of slime today. This is so exciting. All right, hold that up to the camera. Look at this, you guys. We have made some very blue slime. What does that feel like? Kind of sloppy.
Slippery and soft.
Okay, and one can say, you guys, if you look at this slime, we hold it up again in our hands. This looks considerably different than the borax and the glue solution separately, right?
I would have to agree.
We've made a polymer, we put those units together. This is really, really exciting. Okay, now I want to talk about a few things you can do at home that go along with the slime. You probably don't just want to make it for one time, right? You might want to play with it or use it at other occasions. In that case, what you're going to want to do is you can save your slime. And actually, I'm going to go ahead and touch it a little bit too. This is so fun. And what you're going to want to do right here is try your best to get the liquid out, because then it's going to save a little bit better. So we're kind of like shaking that liquid out a little bit. What you're going to want to do is save this in a Ziploc bag. When you put it in a Ziploc bag, it keeps it airtight. It helps to keep it from molding, which is really, really important here. And so we're going to put our slime into a Ziploc bag, and we can put that, most importantly, in the refrigerator. You're going to want to put this in the refrigerator so that it doesn't grow mold. But really, really fun. We'll hold this up here and show it one more time. We've got our slime here. Again, you can make this any color you want. You can make white slime if you want. You can also add glitter if you want to get super exciting with your slime. All it takes: borax solution, glue, water, and food coloring, and now you've made slime. Super exciting. And not only have we done that, we've demonstrated the concept of polymers. What are some interesting uses of polymers in today's society, Dr. Kevin?
Styrofoam would be one, a great insulator.
Yes. And styrofoam is simply a polymer made up of individual styrene molecules, but we've all used styrofoam to keep things cold. Let's see, what's another example?
Kevlar.
Kevlar vests, which we know that the police use and the Army military to stay safe. That is another polymer. There was one other one that you thought of.
Polyethylene.
Right, which is?
I use that to make orthotics.
There you go. So polymers also have a lot of uses in medical equipment, which is really exciting for Kevin to be here, because he works with these. He also works with something called a biopolymer, where you're beginning to mimic polymers in the body in some ways, or use those properties. Can you just briefly explain a biopolymer?
So a biopolymer, in the way that I use it, is typically used as an anchor in bones, but it actually will turn into bone itself because it has the base materials that a bone is made from.
It turns into the bone itself.
Turns into bone itself.
That is remarkable. And in many ways, even though this was like a crazy simplistic demonstration, I mean, it's the same concept. There are small monomer units, there must be, that then go together to help make this bone. So this is great. Fantastic. Okay, that's the end of our first demonstration. Our next one is going to be a little bit more exciting. In order to do, well, that was exciting. I shouldn't downplay the slime. The slime was very exciting.
It has more lasting value.
Yes.
You can keep using it.
That's right. That's right. This elephant toothpaste, we're ready for that. Perfect. So many of you probably have seen elephant toothpaste before. Of course, I'm talking about the chemistry experiment, not the actual elephant toothpaste. However, it may look like that when we're all said and done. So this next experiment is one that you're going to need to be careful. You are able to do this experiment at home. It generates a lot of heat. So you're going to want to be, use gloves, goggles, and not get too close to it when you're doing this at home. What we're going to do for this experiment is we're going to explain our ingredients. We're going to talk about the chemical reaction that's happening in this experiment, and then we're going to do it. And Dr. Kevin and I are going to have to step away because, as I mentioned, it generates a lot of heat. My dog is highly involved in this production this morning. I apologize. Okay, elephant toothpaste. What are we doing here? We're starting with 30% hydrogen peroxide. And what's the molecular formula, Dr. Kevin, for hydrogen peroxide?
H2O2.
H2O2. That sounds a lot like another molecule that we're probably familiar with. What's that?
H2O, water.
Also known as water. So if you take water and you add one more oxygen, you actually get hydrogen peroxide. Now, if you're doing this at home, this is 30% hydrogen peroxide. This isn't the hydrogen peroxide you can get at a kind of a local pharmacy. You actually have to go to a beauty supply store. It's used for bleaching of hair. We're going to use roughly 90 milliliters of this hydrogen peroxide. And so what I'm going to do now is I'm going to pour this 90 mils into our larger graduated cylinder. Now, I'm not doing this all up to code because really I should get eye level, right, Dr. Kevin, with the meniscus here to make sure we're getting exactly 90 mils. Looks
Correct.
Pretty good.
We're at 91.
Okay, acceptable. Okay, this is our 30% hydrogen peroxide. Now, to get fun and fancy to this hydrogen peroxide, we're going to add some dish soap. This is just regular dish soap. There's absolutely nothing special about it. I chose Dawn, just happens to be what I have. Remember, the color of the dish soap doesn't matter. It's simply the fact that we're going to put it in here. So go ahead and add that now, Dr. Kevin, to our hydrogen peroxide. Great. We can make a hypothesis, perhaps, about why we're adding dish soap to this hydrogen peroxide. What do you think might be a reason?
To help it form more bubbles.
Exactly. That leads us to actually talking about the chemical reaction. Inside of here, we've got our hydrogen peroxide. What we're going to do is perform what's known as a decomposition, or a breaking down of that hydrogen peroxide into two harmless components. We're going to decompose this hydrogen peroxide. We're going to make water and oxygen. So the greatest part, kids, about this experiment is it doesn't make anything harmful. You're going to see some gas coming off of this. That's simply oxygen gas. The dish soap is going to help capture those oxygen bubbles to make bubbles. And nothing about this is harmful other than the extreme amount of heat that it's making. Now, what do we need to add, Dr. Kevin, to this hydrogen peroxide to make the decomposition happen?
Potassium iodide.
Potassium iodide. Potassium iodide is going to be considered our catalyst. It's a special chemistry word for a molecule that helps you get over an energy barrier. We think about chemistry as having reactants and products. And what the catalyst does is reducing that barrier. It's making the mountain smaller so that the chemical reaction can happen more easily. Now, if you're doing this at home, instead of potassium iodide, you might use yeast. You can use yeast at home as your catalyst. If you're not able to get potassium iodide, it's a kind of a chemistry ingredient, so we may not need that. Before we add the potassium iodide, we're going to go ahead and put in our food coloring. So let's put in some food coloring here. Again, we're just adding the food coloring to our hydrogen peroxide mixed with dish soap. Dr. Kevin's getting really fancy now here with the food coloring. Very exciting. And to this, we're going to add our catalyst, or our potassium iodide, to force or cause the decomposition of the hydrogen peroxide into water and oxygen. At this point, we're going to step back because, as I mentioned, it generates quite a bit of heat. So keep your eyes peeled on the top of this container here, and we're going to see what happens. I'm adding the potassium iodide now. You can see it's mixing. Here it comes. We've got a reaction happening. Watch that bubble. It's really hard to see. There are so many bubbles happening here. It's like millions and millions of bubbles happening at the top here. And look how now it's starting to form this really nice foam. This is where you're getting that concept of elephant toothpaste. One could imagine. Look at this. Look at this huge bubble forming here at the top. You can see now, and here you go. You're seeing some steam here. As I mentioned, this is creating a lot of thermal energy, a lot of high temperature as one of the products, heat. And here you can see we've got the bubbles here. I'm not going to touch it. It's still very, very hot, but you can see it's all kind of foamed out here towards the bottom. Here it goes. It's still going. If you were to get really close here, you could feel, I can feel the heat coming off here. Here's another bubble coming out. Let's remind ourselves what's happening here. We're decomposing hydrogen peroxide into, huge bubble here, into water and oxygen. Look at that bubble. Here it goes. When is it going to pop? So we've got our decomposition reaction. You could see, like, in a kind of fantasy way, how this could be considered, you know, elephant toothpaste, if you will. I really want to pop that bubble. But again, oh, there you go. You got some steam coming off there. It's still going. It's still reacting. At some point, the chemical reaction will stop. But again, this is showing us how we can use the concept of a catalyst to promote.
It's a great bubble.
It's a great bubble. So this is our elephant toothpaste. Did you have anything to add to this, Dr. Kevin, about, let's see, decomposition, hydrogen peroxide? Oh, we're all very familiar with hydrogen peroxide in the sense that you probably use it to disinfect cuts and scrapes.
Yeah.
I mean, it's highly reactive kind of in and of itself. And so that's really, really nice. There you go. You got some nice steam coming off there.
First cleaning of a wound.
There you go. So, and what you can do is you can very easily, if you want to know these recipes, you can very easily Google elephant toothpaste. If you have more specific questions, you're welcome to reach out to me, and I can provide that for you. I'll spell my last name at the end. Okay, so we're about to run out of time. What we want to do now, I can get it, is do our dry ice, because everyone loves dry ice. Am I right, Dr. Kevin?
Love it.
It is exciting,
especially
and
around
fun.
Halloween.
What did I do with that bowl? Oh, Halloween is a great time to be looking at dry ice. Let's go ahead and really load this up. We are very fortunate. Dr. Kevin was able to get some of this dry ice from his hospital that he works at.
We're shipping bone in it.
So they were shipping actual bones for medical purposes. Maybe you guys can see this. Can you see this foam hopefully pouring out? Let's see. Let's raise this up here. There's just this. Now, what's happening here? This is not CO2 gas. This is
CO2 gas.
What am I trying to say? This is not
liquid.
Yes, exactly. Go ahead and hold up a piece of solid. So dry ice, first of all, is also called CO2 or carbon dioxide. What you're seeing here, if you can see it, we've got a solid piece of the CO2, and it's going directly from a solid to a gas. And what's that called? It's a special phase change.
It's called sublimation.
So we're seeing a very special phase change directly from a solid to a gas. Now, and in fact, I actually was right. You're not actually seeing the CO2 gas. This is actually the CO2 freezing. CO2 gas is colorless. So the CO2 is actually freezing the water vapor. I was on the right track, but had to. Okay, so we're seeing the water vapor being frozen. And again, this is a very special quality of CO2. You know, something like water, if we were to, yeah, can you see that maybe? If you were to see water, if you were to take a chunk of like an ice cube, and I should have done that. If we took a chunk of ice and we put it out in the room temperature, it would first form a liquid, right? We'd see the ice melt before it would eventually go to water vapor. The CO2 completely misses that because it goes directly from the solid to the gas. This is why we call it dry ice. It never goes through the liquid. Really, really cool. I really hope you guys can see this. We're getting to the end here. Keep in mind, of course, that you can get dry ice at a research store. You can get it. You want to be very careful. Do not touch it with your hands. Certainly don't put it anywhere near your mouth. But you can use this. It's a very cool property of CO2. Medical doctors use this for many different purposes. Let's see, any lasting remarks on the CO2? Oh, if you were to take a chunk of the CO2 and put it into some water, it would actually form an acid. It'd form carbonic acid, which is really exciting, H2CO2, something just fun to mention. We're rounding out our time now. So just to recap, we learned about slime, two monomers coming together to make a polymer. You're able to easily do that at home. We also did elephant toothpaste, looking at the decomposition, reaction of hydrogen peroxide using a catalyst, potassium iodide. And then finally, we did CO2 dry ice, and we talked about how this is a very special quality of CO2 going directly from a solid to a gas. I'm Dr. Iski. My last name is spelled I-S-K-I. You can find me on the Tulsa website. We want to thank Dr. Kevin. Any last words?
Thanks for having me, Dr. Iski. It was a great learning experience.
Anytime, anytime. We had the best morning with you guys. I hope you enjoyed these chemistry demonstrations. For any more questions, please find me online. And of course, you can find all of these experiments on Google. Thank you very much. Have a great morning.